In this first lecture, what I want to do is go over a couple of basic concepts in mathematical epidemiology. And so I'm going to use two main illustrative examples. The object is not to cover a lot of grounds. There will be plenty of time in the rest of the course for this, but just to give you a sense of some of the problems that arise. So what I'm going to do is I'm going to cover quickly what are called compartmental models, which is a sort of more general class of models than just epidemiological models. I'll talk about the Kermack and McKendrick SIR model and the SIS model, but I'll take a little detour on the side of incidence functions and as well as an application of MathEpi in terms of what's called maybe herd immunity that everybody's heard about. So to begin with, compartmental models. So compartmental models, essentially now they have become synonymous with MathEpi, but they're much more general than this. And interestingly, it's another type of models that they underlie all the work we do in MathEpi, but people have forgotten that in the 70s and 80s in particular, there was a lot of work done on that type of models. And in particular, John Jacques and Carl Simon, a guy called G.G. Walter, are people that contributed some very interesting results in this domain, Jacques and Walter in particular. And I would say it's a topic that's unjustly forgotten to a large extent. I mean, we all use compartmental modeling ideas, but there are some more general ideas in compartmental models that people sort of reinvent all the time. So what's a compartment? That's the definition that I'm putting here is from Jacques, and as I've pointed out in the intro lecture, you can click and that will take you to the paper in question. So a compartment is an amount of some material which acts kinetically like a distinct, homogeneous, well-mixed amount of material. And so in view of that, we think of susceptible individuals as being homogeneous, well-mixed, etc. And that is one of the limitations in the sort of general epidemic models, the basic epidemic models that we will look at. And then a compartmental system consists of one or more compartments which interact by exchanging whatever material that you're thinking of. And of course, we're thinking of individuals, but compartmental models really, for instance, became very, very popular when people started to look at drug dynamics in the 80s. And compartments may have inputs. They may have inputs from outside, from inside, so from other compartments, and they also can have excretions. And so essentially a compartment looks something like this. It's a box which contains, so here QI is the size of the compartment. So we will be looking at compartments that are made up of humans, but it could be how much material of whatever kinetically homogeneous material is present, you're looking at is present in that compartment. Then you have transfer functions into and out of the compartment to other compartments. And these are functions. Typically, they can depend on the density QI or the density of the other compartments. There's an excretion coefficient or function, which represents how material leaves the compartment towards the external environment, not the other compartments. And there is an input from outside of the system, which can be assumed to be a function of t. It can be quite generic. Okay, and the aim of compartmental models is to generate, investigate properties of the models given connections between the compartments. So this is it's essentially, it falls within the realm of what we call large systems typically, because, and that's where the results that are interesting from the 80s come from. They people tried to look at these problems from a very generic point of view and try to establish properties of compartmental models given the type of connections between compartments and so on. Okay, so, and this is the base. Okay, so the reason why I'm detailing this is that every single epidemic model that I'm going to talk about now and in the next lecture, and a lot of the models you will see are compartmental models, essentially. Now, this model I spoke of yesterday, and by yesterday I mean in the previous lecture that you might be watching on the same day, so this is a little irrelevant, the timing, and that's the Kermack and McKendrick model. And I mentioned in the intro lecture that the Kermack and McKendrick model is a very particular case in a series of papers that Kermack and McKendrick wrote. And here I've listed and linked all of those papers. So the one we're looking at is that first one here, Contribution to the Mathematical Theory of Epidemics, which is the most well-known of those papers. And as I pointed out, even within that paper, the model that I'm going to detail is just a particular case. They've done a lot of work with much more general models than just the one I'm going to show you. But then it's that particular paper from 27 is followed by 4 other papers, which all start with a title of the form Contributions to the Mathematical Theory of Epidemics. And then there's number 2, the problem of endemicity. Number 3, further studies of the problem of endemicity. And then they have 2 case studies. And as I point out, so this is over a period of 12 years. As I've pointed out in my intro lecture, these are really interesting papers, worth reading in their own right. So what underlies the original problem that Kermack and McKendrick considered in their 27 paper is the following. Essentially, their question is, what is the size of an epidemic? And I made that distinction in the first lecture, that there is epidemics and endemics. And here we're really thinking about epidemics. That is some event during which the number of cases of the disease shoots up and then falls back down, essentially. And the idea behind their Kermack and McKendrick work is, well, suppose we are interested in this. So the question is there always an epidemic peak? And when it takes place, how bad is it? And the sort of correlated question to this is, when an epidemic moves through a population, does everybody end up infected? And that is what we call the final size of an epidemic, the percentage of the susceptible population that is affected by the epidemic. That is the final size. Now, the general setup for the Kermack and McKendrick model is quite simple. So they assume a closed population in the sense that there is no inflow into the population nor outflow from the population. They assume that individuals can be in 3 states. There are individuals who are susceptible to the disease, and that means they're not currently harboring the pathogen and they're naive to the pathogen. They haven't contracted the pathogen yet. Individuals can be also infectious and infected with the disease. If they have contracted the disease, then they're actually actively spreading that disease. And this is a simple model. So we don't assume that there is any difference between being infected and being infectious. And more elaborate models will make a distinction between these two states, but here we're assuming they're the same. And finally, there are individuals who can be removed from spreading infection. And that is also something that is going to change in other models. There are two ways to consider removal or recovery. So in the Kermack and McKendrick model, we make no distinction between the reasons for removal. So you're removed from being infectious, essentially. So you are at that point not actively spreading the disease. This can be because you're cured, okay, you've recovered from the disease, or you died from the disease, or you died from other causes. And the model makes no distinction between this, whereas more modern models will typically consider, for instance, a distinction between death induced by the disease-induced death, and natural death. And we'll come back to that later. But so this is the setup, and that means that we have three compartments in the sense that I was explaining before. And the aim of the modeling process is to describe the evolution of the number of individuals in each of those compartments. So for some of you, this is a very natural, this is very, you've seen this already, but for those who don't know, let's go through the process in detail. So first of all, in terms of notation, what I'm going to do is I'm going to introduce three different compartment types, and I'm going to denote these compartments as S, I, and R. Just a remark in passing, the sort of British tradition, it tends to use X, Y, and Z. The continental tradition is more, continental Europe, I mean, is more geared towards, let's say, analytic proofs, but is more clear in terms of notation. I personally don't like X, Y, and Z as notations. Okay, it doesn't matter what you call your variables, but I think there's enough complexity in the models that S, I, and R for susceptible, infected, and infectious, and removed is more explicit and easier to deal with. But that's a matter of personal choice. And finally, of course, we also can count how many individuals there are in the population, and that's just the sum of those three variables. And I should point out that we are going to formulate a differential equation, and therefore what we have is, we are going to use those variables as depending on time. Okay, so they are functions of time. And as with all differential equations, what we have is a time-dependent solution. Okay. Now, there's no demography in this model. And the reason why we don't consider demography is that we suppose that the time interval over which we work is sufficiently small. So we say also there's no demography or there's no vital dynamics. This is, of course, an assumption. It is valid in many contexts, okay? If you think about what's happening at a country level over a period of, let's say, 6 months, the numbers are not going to change. Of course, there are births and there are deaths, but overall, the global population of a country doesn't change that much over a 6-month period, for instance. We assume that the incidence is of mass action type, and I'll come back to incidence functions in a while. And we assume that the incubation period is short, we actually are going to neglect it altogether, and that the infection has a limited duration. So you do not remain infectious for your entire lifetime unless you die from the disease before you recover. Okay. And so what we have is what's called a flow diagram that allows us to summarize this information that I was just explaining. So a flow diagram just represents the potential trajectories for each individual in the population. So essentially, you can start susceptible. And if you get infected because you come into contact with someone who's bearing the disease, then you will progress into this second compartment, I, in which you will be making contacts with others, you'll be infectious. And after some time, you might progress out of this compartment and end up in the removed compartment. Okay. And what I'm showing here are the rates. So we're formulating a differential equation. And so these are going to be rates, but I'll come back to that in a second. Okay, so the first thing I really want to stress is this flow diagram. The flow diagram is really useful as a way of thinking about the problems that you're looking at. You will see more elaborate models will have different flow diagrams, but for instance, if you're a mathematician talking to an epidemiologist, flow diagrams are very useful because they allow you to have a common language, essentially. And likewise, an epidemiologist wanting to explain something to a mathematician, a flow diagram is a very useful tool. Okay, so let's see how this works. So I've put the flow diagram there on the left. And the idea is that I'm going to formulate a differential equation. And this first one, I'm going to spend some time explaining. Later equations I won't. So, as I said, the unknowns are the state variables, what we call the state variables. So that's the number of individuals in the compartment at time t. That S of t, I of t, and R of t. These are the unknowns in the problem. And what we do is that we say that these quantities vary as a function of the different processes that act on the compartments. So here, for instance, we're writing that the number S of t of individuals in the susceptible compartment, it changes, okay, this is a derivative, it's a derivative with respect to time, t is going to be time all the time. So S of t changes in the following way. It changes because people become infected, and they become infected by contact. So if I'm a susceptible individual in the S compartment, if I come into contact with an I individual, so an infectious individual, then I'm going to move from S into I. Okay, and remember I said that the population is closed, so there's no inflow of new susceptibles, there's nothing else. So in terms of the susceptibles, all that can happen to them is maybe they'll get infected. Okay, and if so, that rate here, just in passing, this is the incidence rate. I mentioned in the first lecture that there was sometimes some mistaking different terms. So I of t is the prevalence of the disease at a given instant in time. And this rate here is the rate at which new infectious individuals are created. And so per unit time, that is the incidence rate. Okay, so upon infection, I move on to the I compartment. And in the I compartment, it's the same. I want to balance what's coming in and what's going out. So what's coming in is those new infectious, okay, beta Si. So this is the term here, beta Si of t. But at the same time, there's an outflow from this compartment towards the removed compartment. And that outflow happens at the rate gamma. Okay. We say it's a per capita rate because it's multiplied by how many individuals are in the compartment at time t. Okay. And finally, those individuals who leave the I compartment end up in the R compartment. Okay. So this is a system of three ordinary, well, I mean, it's an ordinary differential equation. It's a system consisting of three equations. It's non-linear because of this term S times I, S of t times I of t. Okay. So it's a complicated problem. Just the fact that it's non-linear makes it complicated. Typically, we consider it with initial conditions. S of 0 equals to some value, S0, I of 0 equals I0, and that we typically assume that I of 0 is small because that's the setting at the start of the epidemic is essentially we'll have most people susceptible, a few infectious, and often we assume that there's no removed at the beginning. So the R is typically 0 at 0. Okay. To simplify things, it's very common with ordinary differential equations to, first of all, instead of writing dx of t over dt, we write x prime of t. But even further, we omit the time dependence. So in practice, we write x prime. So here we have s prime of t equals minus beta si. So I've removed all the time dependence, and this is something you have to bear in mind. I mean, if you're not familiar with ODEs, this is something you have to bear in mind. This is still a system of differential equations in which the independent variable time is still present, but I'm just not showing it. But the solutions I'm looking for, S of t, I of t, and R of t are functions of time. Okay. So again, it's considered together with initial conditions that are those that I described before. Now, if you look at the system, one thing you can see is that removed individuals, they don't play a role in the dynamics of the problem, if you want. Okay, if I look at these equations, I can see that you see that S is involved in those two equations, I is involved in the three equations, but R is only involved in this last equation. Okay? So in a way, once I know what S of t and I of t are, what values they have, I can reconstruct the value of R of t from these two values because, and that's the second part of the argument, if you look at the total population, N of t, you realize that when you take its derivative, that derivative is 0. Okay, and you can see that by just summing the right-hand sides of these three equations. You see that minus beta si cancels out with the beta si here, and that minus gamma I cancels out with this gamma I. Okay. So the sum of the three right-hand sides is 0, the sum of the left-hand sides is n prime. So the fact that n prime is equal to 0, you know that if the derivative of some quantity is equal to 0, that quantity is constant. So that means n is constant, and that and the previous argument means that it can essentially recuperate the dynamics of R from the knowledge of the dynamics of S and I. Okay. So from now on, instead of considering the three differential equations, I'm going to look at two differential equations, that minus beta si and beta si minus gamma I. And before I go any further, let me just make a remark here, because it will be important throughout the models you do. So this is a rate at which new infections are created, and I pointed out that this is what we call a per capita rate. And I'll just point out that this per capita rate gamma I means that the average time of sojourn, the average time of residence of individuals in I before they move to R is 1 over gamma time units. Okay, so I'm not going to go into the details of this reasoning, but it's a classic property. That's important. When you have a so-called per capita rate in compartments, this means that the time of sojourn in the compartment is 1 over this rate. So, what do we do with this model? So if you have little experience, very little, I mean, experience with systems of differential equations, this is going to be a crash course in what you would do. So if I have a system like this, typically the first step is to look for equilibria. And equilibria are solutions that are constant. Okay, and I find them by assuming that I have constants. Okay, so if I suppose that S prime equals I prime equals 0, this means that S of t and I of t are constants. Okay, are constant. They don't change the same way as I described here, the fact that the total population doesn't change. Okay, so I look for equilibria by setting S prime and I prime equals 0 and trying to see what that means in terms of the right-hand side. If that equals 0 and that equals 0, then what happens? Well, from that second equation, I can see that if I set beta S minus gamma times I equal to 0, these are scalars. Okay, so the product of two scalars equal to 0 means that one of them at least is 0. So either beta S minus gamma is 0 or I is 0. Beta S minus gamma equals 0 means that S must be equal to gamma over beta. Okay. Now, if I substitute these values into the first equation, okay, I'm looking for the S and the I such that S prime equals I prime equals 0. So when I substitute these values into the first equation, I get, in this case, that S and I must equal to gamma over beta and 0. Okay, that's a good case, let's say. Okay, in the sense of the mathematical analysis, I should point out. In the second case, what you see is that if I put I equals 0 in this equation here, in equation 2a, well, any value of S is works because I'm multiplying two scalars together, well, three scalars with beta as well. I'm multiplying numbers together, and one of them is 0. So I can take whatever value I want for S, and I still have a 0. And that is a problem. Okay. In terms of computing equilibria, the analysis that is typically done, this poses a problem because that is what we call a non-isolated equilibrium. Because any S on the S-axis is an equilibrium. So when I equals 0, the entire positive or non-negative S-axis is an equilibrium. And that means the typical techniques that you might have seen, I mean, for those of you who do math, you have seen, but for those of you who are less mathy, perhaps you have seen the linearization around the equilibrium. That doesn't work here because it doesn't work fully because of this non-isolation of equilibria. Okay, so this is just a remark in passing. But we can still do things. So there's a little workaround that is that you can find in the paper of Kermack and McKendrick. So they realized this themselves, and it is that if you consider the dynamics of di over ds. So if I compute di over ds, remember that di is the derivative of I with respect to t. ds is derivative of s with respect to t. Okay. So this essentially is saying what's the equation for I prime over s prime. Okay. So I take the equation for I prime. I take the equation for s prime, and I get an expression. Okay. Which of course is written in the wrong direction. No, it's in the good direction. I always make it plus minus 1. Okay, good. So I get this expression. And this is this is the derivative of I with respect to s. And I have an expression that just involves s. So this means that I can integrate this. Okay, this is a differential equation. Time has disappeared from this equation in a way. I mean, it's the derivative of I of t with respect to the derivative of s of t, with respect of s of t. Okay, so time is there, but in an implicit manner, essentially. Okay. So you can integrate. And when you integrate, you find a solution like so, which expresses the variation in I as a function of s. Okay. So this gives me trajectories in the IS plane, that I'm going to show you in a second. So first, as always with a differential equation, you substitute the initial condition to find the integration constant. That gives you I of s equal to this. Recall that I can also recreate R if I need, and I find it to be equal to this. So as a function of s, I of s changes this way. Okay. So if I plot this in the SI plane, okay, so this is the plane of susceptibles and infectious. And remark one thing, because the total population is constant, I can normalize things, which means that I can make the total population equal to 1 and consider the proportion of susceptibles and infectious in the population instead of considering the numbers. That's just going to be useful here. Okay, this is just to show you the general context. In general, I don't always recommend doing this, but here this is a very simple model. It's okay to do this. So what we find is that we find these trajectories in the plane SI, and starting from those dots, okay, the dots are the initial conditions. So I can start with S more than a half, etc., and very low I, or I can remember that S plus I, because I've normalized my population, the 2 equal 1, the sum of the 2 equals 1, essentially, because I'm assuming I start with no infectious, removed, and so I can follow these solutions. And what you can see is there's two different behaviors here. There are some, all the red ones, I start with a certain value of I, and then I increases and then decreases. Whereas the white ones all have I always decreasing. And I mean, this is a very sort of arbitrary example. This is not exactly what we'll observe in real life, of course, because here I've set this ratio beta over gamma to a given value, and I'm playing with the initial conditions. In real life, the initial conditions probably represent your population. So S of 0 would be essentially the total population, or the total susceptible population at the start of the epidemic, because you might have initial immunity for some, but the total susceptible population will be S of 0, and I will be very small. So what I'm showing here is not the way you would use the system in real life. But it is illustrative to see that some of those solutions go through an epidemic, okay? Because essentially what's happening is that the number of infectious grows and then falls. But you see all of them fall. This is the number of infectious, of a proportion of infectious in the population. And you can see that they all end up with no infectious. But the way they do so is going to depend, in this particular case, on the initial condition. If I is large enough, they'll just collapse. Whereas if I is smaller, I first go through an epidemic. Okay. As I said, this is not how you would use the model, but nothing forbids you from using it like this. But in general, that's not what you do. So what this shows and is that this ratio here, and I should point out it's appearing here. So, well, it's the opposite of that ratio, the inverse of that ratio here, okay? But that ratio is quite important. And so we are going to call it R0, and it's the basic reproduction number, in the way it's called. And now everybody, thanks to COVID-2, everybody's heard about the reproduction number, but so that's how it's defined in this particular case, okay? It's the ratio of beta, which is that infection coefficient, and gamma, which is the rate of removal. And just in passing, what that means is that this is beta times 1 over gamma, and 1 over gamma, remember I said this is the average time you spend in I before moving to R. So what this is saying, it's essentially the probability of infection multiplied by how long on average you're infectious for. Okay. It's this simple here because I've normalized to n equals 1. Okay. Otherwise, normally I should multiply this number by S0. And so what we get is a result like such, like so. So if I have a solution to my system in proportions, and I'll stress this is the result in proportions, and I define R0 as beta over gamma, then if R0 times S0 is less than 1, then I of t goes to 0 when t goes to infinity. If R0 is times S0, so remember that I said if I don't normalize, I'll multiply by S0. So what happens in that case means that R0 is greater than 1 and R0 is less than or equal to 1. But if R0 times S0 in this normalized case is greater than 1, then first I reach a maximum, and I can compute this maximum explicitly. Then I goes to 0. Okay, so this is what this is saying here. But this is the R0 times S0. So in this case, what I have is that R0, the red curves are the situation where R0 times S0 is larger than 1. I first reach a maximum that I could compute precisely along these curves, maximum of I. And then I go to 0. Whereas if R0 times S0 is less than 1, which is these white curves, then all I do is decrease to 0. Okay. There's another interesting property that we get from this result, and it's in terms of the final size. So let me detail this for a second. So you can see that the result also states that the proportion of susceptibles is a non-increasing function, of course. Okay, so if you follow these curves, you can see that there is no going back and forth. I should make sure I'm not going anything else than towards the left when I follow S. Okay. So S of t is a non-increasing function, and I can find its limit. And that limit is the only solution of this equation, which is a transcendental equation. Okay, it involves, if you want to solve this, you could take the exponential, for example. So that's what it's called, a transcendental equation. But in this case, I know that this equation has a unique solution, and it's somewhere in between 0 and 1 over the R0 that we've defined. And this is useful. Remember the question, one of the underlying questions was, what is the final size of the epidemic? Well, if I want to consider this, I need to consider S of 0 minus S of infinity. And that tells me how many people got infected. So S infinity is how many people are still susceptible when the epidemic is over. Okay, so S of 0 minus S infinity tells me how many people got infected during the course of the epidemic. So let me take a brief detour now on incidence functions. So there's a very good paper for this. I recommend reading. It's in Trends in Ecology and Evolution, and it talks about how to model pathogen transmission. And so what I'm describing here is a mix of things in that paper and sort of personal remarks. The first remark I want to make, and that is not in that paper, is you'll see two formulations, two terminologies. One will be to use what are called incidence functions, where that's the most common way of doing things. But you'll also see force of infection. And let me explain briefly the difference. It's a very, very simple difference. If I have my S prime equation, and it takes this form, S prime is minus some function of S, I, potentially other variables, potentially the total population, I don't really know, okay, but a bunch of things. This is what we call an incidence function. Whereas if I have S prime in the form of minus lambda, lambda is typically what's used in that case, but it doesn't matter, okay? A function of the same, but times S, okay? Instead of having the S hidden in here, I have, it can play a role here, but it's also outside, multiplied by this function lambda. Then lambda is what we call a force of infection. And essentially, they're used interchangeably, except that you'll see this form, for example, this latter form, the force of infection, in PDE models, for instance, or age-structured models. Well, I mean, most of them are PDEs, because essentially this is showing how much, well, it's, as the name implies, it's how infectious the rest of the population is to the susceptibles. And in advanced PDE models, or advanced models in general, this is something that we'll try to take in, that will be more complicated than just multiplying S by I. Okay, so we might see examples of this later, not in this lecture. Okay, so in general, what's a force of an incidence function? So here I'm looking at incidence. So it's a function of the susceptible and the infectious, at least, and potentially the total population and whatever else is in your model. Like if I write it this way, I'm hiding a few things, and that is that if you think about infection, essentially there's two things that must happen. There's, well, how much infection is happening. I need to be able to count how many contacts are taking place. Okay, so I have some susceptibles, I have some infectious, and I want to know how many contacts take place. And then whenever there's a contact, what's the probability that that contact results in disease transmission? Okay, so essentially the two components that are coming in are the number of contacts and the probability that a contact is infected. The product of these two gives you the incidence. And choosing an incidence function is really complicated. And those of you doing, for example, agent-based models, that I'll talk about briefly in the next lecture. No, that I talked about briefly in the introduction, sorry. So those of you doing agent-based models, that type of model, the main purpose of agent-based models is to address some of those approximations we make when choosing incidence functions. The two most used functions are mass action incidence, beta SI. So this the term mass action comes from chemistry. The idea is that if you have S of T susceptibles and I of T infectious in the population at time T, remember, this is a compartmental model. We're assuming everything is well mixed and etc. So that means that there can be S times I contacts per unit time in this population. And then beta here plays the role of a coefficient that says what proportion of those contacts are actually infecting. The other form that's used a lot is a beta SI over N. So in that case, we're dividing the number of contacts by the population that is present. And so the interpretation of beta, and I'll say a word about this in a second, okay? But the interpretation of beta changes. So I recommend usually, but it's not a requirement, it's a recommendation, to just call it the disease transmission coefficient, because the interpretation changes whether it's this or that, the first form or the second form or other forms. But that's just my personal liking. Okay, so mass action incidence, to go a bit more into detail, this is a strong hypothesis. Remember, I said this assumes that every susceptible comes into contact with every infectious. That's the number of contacts that can take place. So there's a lot of debate about this, but one interpretation you can make is that this is valid for small populations, because in a small population you can assume that yes, it is indeed true that every susceptible could come into contact with every infectious. Think about a classroom, for instance, or something like this. Clearly everybody's in contact with everybody else at some point. When populations become larger, it's a bit more of a problem, and so that's when we start using proportional or standard incidence, and in which case we divide by the total population. So here the assumption is that every susceptible individual meets a fraction of the infectious individuals, or vice versa. It can be also every infectious meets a fraction of a susceptible. And there's an interesting paper of Hevcott in '76, which has some discussion about the role of considering S over N times I or S times I over N. Typically, you could assume that this is the case of a larger population. Now, one important remark, though, is that in practice, if the population, the total population is constant, N, then if it's constant, then the two are identical. Okay, let me show you how this works. So suppose that N of T is some constant, then I can write that beta SI is equal to beta tilde SI over N, and that means that if I take that beta tilde equal to N0 times beta, then that expression is the same as this one, essentially. Okay, so in terms of the dynamics, there's no change. So when you have a constant total population, you shouldn't really worry about which form of the incidence function you're using, between those two, I mean, because they do the same thing. They have different units. That is important. And let me just make a remark here. And this is a thing, I think it's more for the math people in the audience than for the more practical people. Units are important sometimes. And so if I have x of t, that's the population in a compartment at time t, then x prime, the units of the derivative, are number per time. Okay, it's d over dt of x of t. X of t is number, d over dt is per time unit. Okay. And of course, when I'm writing a differential equation, what I have on the left must have the same units as what I have on the right. So if I have mass action incidence, it's beta SI. S is a number, I is a number, and beta is the thing that I'm looking for the unit of. Then I get that beta SI is beta times number by number. That means my units for beta have to be, I need this to have units number per time. So beta in this case must be 1, so per number per time. Okay. So whereas if I have beta SI over n, this is number, this is number, this is number. So I have beta times number divided by number, that's beta times number. So here my units are number per time if beta is per unit time. Okay. And if you're using this reasoning, this is something you have to bear in mind. And that's why I made the remark earlier that I prefer to call beta the transmission coefficient rather than give it a name that implies what type of units it has, because the units are going to really depend on what you are doing with the system. Another type, so we've seen standard and mass action, but another type is what's called general incidence. This is a very good function if you have data fitting in mind, because not only can you vary beta, but you can also vary this p and this q. Okay. And I should point out that some of the early results in terms of global stability, so mathematical approaches here, use this type of problem as well, of incidence as well. You can, and I refer you to that paper I was talking about before. There's a whole list. I'm not showing you all of them. You can assume that there is a refuge effect. So a certain fraction of a population is really susceptible. Others are not susceptible, and therefore there is a sort of, for instance, there's a spatial heterogeneity that makes some people not accessible to infectious. So that could be one way to model it. Okay. You can have negative binomial incidence. You can have, this is an example that I worked on, where we consider the switching incidence, the idea being the one that I mentioned earlier, that if you have mass action, this is more appropriate for small populations. If you have standard incidence, this is more appropriate for larger populations. So here, normalizing things, what we do is we say, well, we have mass action when the population is small enough, and standard when it's larger. And when you have non-constant total population, because otherwise it doesn't matter, but we take a non-constant total population by assuming that there's a birth rate that's different from a death rate, and there's disease-induced death as well, then with that type of model, you obtain all sorts of interesting dynamics. Now, let me change gears and move towards the endemic SIS model. So remember, One of the things I was discussing before was the fact that in the Kermack and McKendrick model, we observe two possibilities. Either the number of infectious increases before it collapses, or it collapses right away. Okay, so the alternative, based on that value of R0, its location with respect to 1, the alternative was I have an epidemic and then things die out, or I have no epidemic at all. Here we're going to see a so-called endemic model. Let me explain. So same setup, essentially, except that I'm taking it even simpler. I'm assuming a closed population, and instead of assuming that people are susceptible and infectious and then removed, I'm assuming that once they are removed from being infectious, individuals right away can become infected again. Okay. So there's two compartments. The sum of the population, the total population, is the sum of the two. The infection is limited. There's no incubation, same as before. But here I'm going to change my hypotheses a little bit. So in the Kermack and McKendrick model, I was assuming that there was no change in the population size. Okay, I could neglect changes in population size, whereas here I'm going to assume that there's birth and death of individuals. Birth only happens in the susceptible individuals. Okay, I assume that susceptible individuals, they're born, I should have changed this, this is D, sorry. They're born at the per capita rate D, proportional to the total population. Okay, so how much birth happens depends on how many people there are, because, well, I mean, if you think about it, it makes a lot of sense. The death is also per capita, and it's proportional, in that case, for susceptible individuals to the susceptible population. Newborns are all susceptible. Okay, this is what, if they were not, if some of them were infected, were born infected and infectious, then this would represent the case of what we call vertical transmission. Okay, but we're not assuming that there is any vertical transmission, so all newborns are susceptible. Infected and infectious individuals, they're also subject to natural death. And that happens at the same rate D as birth and death. Okay. There's recovery, the same rate gamma, it's per capita gamma as we had used in the previous model. And we also don't take into account disease-induced death. Okay, so we ignore the fact that the disease can kill you. So what we have is the following flow diagram. So it's a little bit more complicated than the one we had before. So this is, and remember I said this is a typo I need to fix, this is a D here. So this is birth at that rate D proportional to the total population, S plus I. This is infection, and here, like the previous model, the Kermack and McKendrick model, assumes that infection happens at the rate beta SI. Here I'm using beta SI over N. It's not going to make a difference because the total population is constant. But just for illustration, I'm going to use SI over N instead of SI. Now, people recover, and when they recover, instead of being removed and not contributing to infection at all, nor being able to be reinfected, here I'm assuming that right away they can be reinfected. Okay, there's diseases like this. Gonorrhea is a well-known example. You can get gonorrhea, recover, and then right away afterwards you can get gonorrhea again. So there's not that many. A lot of diseases confer at least temporary immunity, but this is not what we are considering here. So recovery takes you back into the S compartment, and in both compartments you can be subject to death, and that happens at the rate D, so DS for susceptible and DI for infectious. And the model is like so. So there's birth at that rate Dn, N is S plus I, okay. There's death at the rate D. There's infection when you go from here, from S to I, okay, at that rate, that standard incidence rate beta SI over N. And recovery takes you back from the I compartment into the S compartment. So in the S compartment, it comes in with a positive sign. In the I compartment, I have inflow of individuals when they get infected, and I have outflow when people die or recover. Okay, and this will be the rule with most ODE models and a lot of other models, okay? Essentially, once you have your flow diagram, it's easy to recompose what the equation should be. If your flow diagram is well written, you have your differential equations without ever even needing to look at the differential equation. So, of course, we consider initial conditions that are non-negative. Typically, we are going to consider the sum of the two must be at least positive, because otherwise we have something completely silly. And I should point out even further that I should probably consider I of 0 to be positive as well, because if I don't, you can see that if I substitute I equals 0 in this equation here, I prime is then equal to 0. Which means that if initially there's no infectious, there is never any infectious in the population. Which tells us that the model is well written in a way, okay? It preserves, I'm not making infectious where there is nobody to spread infection. Okay. But once again, this is not the aim of this model, I mean this course, so I'm by the way, I should point out there are slides that I made and videos that I made for a more mathy oriented version of this course. There's a few links here and there in the slides to these videos and these slides. If you want more detail, feel free to look at those. Now, the model that we just formulated is what we call an SIS model. For susceptible, infectious, susceptible. If there's no recovery, then the model is what we call an SI model, which would be one where the disease is chronic. Say HIV, you never recover from HIV. That would be a very bad model for HIV because it would be a little simplistic, but still it could be considered a model for HIV. As I said, gonorrhea, a lot of bacterial diseases, staphylococcus, etc., have no immunity. This type of characteristic I mean about SIS, not SI. Okay. Let me remark, we're talking about modeling, and so some remarks about modeling more than the math itself. I said birth and death. It's important to realize that in an epidemic model, when you're talking about birth and death, you're talking about birth and death relative to susceptibility, not to the actual total population, but to the actual total susceptible or infectious or whatever population. So for instance, if I'm looking, I was talking about HIV, if I'm not considering mother to child transmission of HIV, if I'm looking for a model of transmission of HIV, the model is going to assume susceptibility starts when at-risk behaviors start. And so birth is not so for example, if I'm looking at drug-induced transmission, I mean needles-induced transmission, well, it's when you start using needles to inject drugs, that you enter the susceptible population. And death doesn't necessarily mean you die, it simply means that susceptible behavior has stopped. Okay, so birth and death are relative in there, and the susceptible population is the one that is susceptible to the disease that you're interested in, not necessarily the entire population of a country or something like this. Okay, so how do we analyze this? And here again, I'm going to play a little trick. Normally, this is a planar nonlinear system. It's quite easy to study because it's planar, but it's a nonlinear system, so we would use the typical tools of analysis. I'm not going to do so here, not explicitly, because the model that I showed you, that SIS model, is actually integrable in the sense that we can find an explicit solution to the system. That is super rare, and you should not assume that this is going to happen frequently. But let me show you, well, some components you would still look at would typically be that one. So it's always interesting to check what's happening to the dynamics and if you of the total population. So when you look at how the total S plus I here, not S plus N, a few fixes to do in my slides. So when you look at S plus I, you sum the right-hand sides of all equations, and what you see is that you have dn minus ds plus I, which is n, so this is 0. Therefore, the total population is constant. Because it's constant, I mean, we can do this trick that I'm showing you here all the time, but because it's constant, that trick is going to work well. So this is actually something that is often useful, even for a system where you can't find an explicit solution, is to go to proportions. So to go to proportions means that instead of considering the original variables S of t and I of t, capital S of t and capital I of t, I'm going to consider variables that are the proportion of these state variables in the population. So little s of t is going to be capital S of t over n of t. Okay. So first of all, when I sum them, I get 1, because the total proportion between the susceptibles and the infectious is 1. And then when I compute the derivative of I see that it's this. Remember that those quantities depend on time, okay? They're not constants. They're I of t, n's of t's, etc. So I get this equation. But n prime is 0. Okay, so this second term here is equal to 0. So the evolution of the proportion of infectious and susceptible, so it will work the same way in the population, is simply the equation for I prime, the original equation for I prime, divided by the total population. So when I compute this, I find this equation. Okay, beta little si minus d plus gamma I. So I've removed the dependence on n here. And when I look at this system in proportion, well, first of all, I can see that S is 1 minus I. Well, I know that S is 1 minus I, so I have this system here. Okay. But when I read this equation, this second equation here, I see that I can rewrite it as so. I prime minus this expression equals minus beta I double. I squared, sorry. So if I set u equals to I inverse, I get minus u prime minus this constant times u equals minus beta. Okay, so I get this equation. And this equation is the Bernoulli equation. Okay. Well, actually, the first one is a Bernoulli. So, but sorry. So the first one is Bernoulli, that one here is the Bernoulli. But how do you deal with Bernoulli? You do this change of variable that I was showing you. You find an integrating factor. I'm not going to go into the details. As I pointed out, well, you have the slides. This is an exception. This works so infrequently that it's not really worth me spending time explaining what to do, because that's never going to happen. But it takes us here. We can compute explicitly, that means there's a function of t, okay, that is solution to my problem. As I said, this is the only example I think I know where this works. So in all the epidemic models that have been published, I think this is essentially the only one that works this way. This is, by the way, you can find this in a paper of Hevcott, another paper of Hevcott in the late 70s. Might actually be the same that I was giving earlier, but never mind. So what you find is an expression. As I said, this is a function of t for the evolution of a proportion of infectious in the population. So my solution is something like this. And here I've highlighted in red this term beta minus d plus gamma, because you can see that it's coming here. So the sign of this term is going to determine whether this numerator is positive or negative. If beta minus d plus gamma is positive, this numerator is positive. Otherwise, it's negative. But if this is, let's say, positive, then this is positive as well. So this means this exponential minus some constant times t, this is e to the minus ct with c positive. So this goes to 0. Okay? And this is negative. This goes to 0 as well. And this one is negative. So you can see that the sign, it turns out the sign never changes. The sign is always going to be positive of the entire expressions. But what's important is that these quantities go to 0 or not. Okay? And so you end up with these two cases. If that beta minus d plus gamma is negative, then the limit of this exponential term is plus infinity. And so S of t goes to 1 and I of t goes to 0. Whereas if beta minus d plus gamma is positive, then the limit of the exponential is 0. And what we have is that the limit of S of t is this, and the limit of I of t is this quantity. And we can rewrite this using the basic reproduction number. So this one has a slightly different expression than the one we saw for the Kermack and McKendrick model, because there's a d here, which is the death rate. Okay, so if we define the basic reproduction number like this, then these conditions that I had in my previous slide, I can express them as a function of R0. And also, these limits that I get here, I can express as a function of R0. Okay, that means that I can formulate a result like this. If I look at my system in proportion, I have the following alternative. If the basic reproduction number is less than 1, then the limit of S of t is 1. That means all individuals are susceptible in the long run. Whereas if I of t and I of t goes to 0, the disease goes extinct. Okay, whoops. On the other hand, if a basic reproduction number is larger than 1, then the limit of S of t is 1 over R0. Remember, these are a proportion of susceptibles and infectious, and R0 is larger than 1, so this is smaller than 1. Okay, so the proportion of susceptibles goes to 1 over R0, and the proportion of infectious goes to the complement to 1 of this quantity, so 1 minus 1 over R0. And in that case, what's happening is the number of infectious goes to a positive limit. So the disease is now endemic. Okay, So that's a big distinction from the Kermack and McKendrick model. I remind you that what we saw for Kermack and McKendrick was that we had a peak first and then everything went to zero. Here, what we have, the R0, tells us the difference between the disease going extinct or the disease becoming endemic. Okay? So R0 is a measure of a propensity of a disease to become established in the population, in this case. And when establishment happens, R0 also determines how prevalent the disease is in the population, okay? Because if I write I star to be that limit, that limiting value of I of t, okay, 1 minus 1 over R0, I can see that when I take R0 larger and larger, this 1 over R0 goes to 0, and that means that we go towards 1. So if R0 is very large, the disease is present in virtually everybody in the population. Okay, and so in this case, control policies, well, what they'll try to do is to reduce R0 to less than 1, or actually to reduce it as much as possible, because even if I can't make it less than 1, the smaller it is, the less endemic the disease is. And again, we see the same thing as before. And I'm not going to explain the mathematics behind this, but the 1 over d plus gamma that appears in this R0 here, that 1 over d plus gamma is the average time, I should go back to the model, is the average time that you spend in the I compartment before you follow one of those two arrows. You see this is d I and gamma I. The sum of the two is d plus gamma I. And this is a result in terms of sojourn times. It's called competing risks. So if you're infectious, you have competing risks of dying or recovering. And the average time spent before one of those competing risks is followed is the sum of the two rates. Okay, so this is what is happening in our R0 here. So once again, R0 is some measure of a probability that a contact is infecting multiplied by the average time you spend infecting others. And so this R0 that we saw, it's very much used in epidemiology, as you know, but in practice, there's also a proper definition from a statistical, a probabilistic point of view. It's that R0 is the average number of new cases generated when an infectious individual is introduced in a completely susceptible population. Okay. The way I've characterized R0 in both cases that I was showing you is more as a purely mathematical construct. But in practice, sometimes you can tie that mathematical property with this probabilistic property. Just for example, measles is a feared disease. These are values that were estimated, they're reproduced in the May and Anderson and May book. So this is where I got these values. These are estimates of the R0 for measles, and you can see, so remember, measles is, once you have it, you're recovered for life. I mean, you're immune for life. So here the susceptible population is only the kids and the non-vaccinated adults. But for those people, the R0 of measles is really, really high. Let me just point out that the model we have seen, here we can use the regular type of analysis. I made the point that the Kermack and McKendrick model, there's a problem with computing what's called the local asymptotic stability of the equilibria because of that fact that I have a line of equilibria. In this SIS model with demography, this is not the case. So how would I compute R0 classically here? Well, just for principle, I'm showing you the model normalized to 1. As I said, I don't do that very often, but here I'll do it. So this is what you get. You compute what's called the disease-free equilibrium. So you compute the equilibria, you find 2 equilibria, you find a disease-free equilibrium, and you'll find an endemic equilibrium. But in terms of computing R0, R0 is computed by finding where the disease-free equilibrium loses stability. So the disease-free equilibrium, because I'm normalized, it's actually just everybody is susceptible, nobody's infectious. Okay, I compute the Jacobian of the system at the disease-free. I find these values. This is an upper triangular matrix. I know the eigenvalues are minus d and beta minus d plus gamma. And this is where we get this beta minus d plus gamma again, because of course minus d is always negative. Therefore, the loss of stability of this disease-free equilibrium is going to happen when this quantity is positive. And we find the same thing. And I'll just mention very briefly, and again, this is not something I'll go into here, but there's a method by Diekman and Hechtebeek originally, but that was characterized in the ODE case by Van den Driesche and Watmore, that I was talking about in the introduction, that considers a much easier way of doing this computation than the classic way. I should point out here the computation is very easy, but suppose I have 6 or 8 equations, I still have to deal with a matrix with 6 times 6. It can be complicated to find the eigenvalues and so on. And the method of Van den Driesche and Watmore allows you to focus on one particular point there and just consider the infected variables instead of all the variables. So in the case of the model that we were looking at, essentially the infected compartment is just the I, and so we formulate this matrix, this vector, but here it's a scalar, okay? Vector F, vector V, we take the derivatives, and we find the reproduction number like so. But as I said, this is not the point of this course, I'm not going to detail this. The result is actually this, that if you've computed the matrices in the way that I sort of hinted at in previous slides, then you find the R0 value as the spectral radius, rho here is the spectral radius, as the spectral radius of this matrix, which is called the next generation matrix. And you get stability and instability of the R0, of the disease-free. And as I said, there's some slides in another course I taught and some videos. If you want more detail, I explain in much more detail how to do this. So where have we got to this far? I'm almost done. We've got about 3 minutes left, or 5 minutes left. So we saw the Kermack and McKendrick model, and in that one, the main question was, do we have an epidemic or not? That was, do we have an increase in the number of infectious? That happened when R0 was larger than 1. Or we had a decrease of the number of infectious throughout the course, and that was when R0 was less than 1. We then looked at an SIS epidemic model in which the threshold this time separated the disease going extinct from a disease becoming established in the population, i.e. endemic. Both cases, we had some way of integrating things. And as I've said, and I'll repeat here again, this is an exception. You should not assume that you're going to be able to do that except here. I wanted to show you this because I think it's a good illustration of what happens in epidemic models. And it's good to be able to do it very simply in this case, but this is an exception. And I'll point out that, and I'm guilty of the same here, we often speak of epidemic models when referring to whatever type of model we've written. And we shouldn't be doing this. When you see that discussion I was just making, we should be talking about epidemiological models or endemic models or epidemic models. We should make the distinction between epidemic and endemic because they represent very, very, very different situations. I mean, in one, I know the disease always goes extinct. I'm just wondering whether it goes through a peak or not. In the other, the disease either goes extinct or is present all the time. So these are very different situations, but yet we call everything epidemic models. Okay, but this is not even something that I try to apply myself. I will say epidemic models sometimes, but never mind. And the last thing I want to do is I have 2 or 3 slides remaining. I'm shooting for an hour and a half and I'm at an hour 25. So this seems to be okay. The last thing I want to mention is herd immunity. And the reason why I want to do this is that this is essentially one of the first cases where epidemic modeling, mathematical modeling in epidemics, has allowed to really coin a concept and really explain a concept. And I think of mathematical models in epidemiology as important, not always in terms of how you fit data and so on, but also to help explain concepts. And this is a prototypical application of this way of thinking. Okay, so let me take the Kermack and McKendrick model essentially, but make it a bit different. I'm going to assume that there is some demography, essentially, but that birth equals death. And I'm not actually going to worry too much about letting things in or out. I should probably in the way I'm writing it, but what's important is I'm going to assume that there's a certain fraction of the population that's vaccinated at birth. Okay, P. Incidence is mass action, so I look at this model here. It's a very simple model. I haven't put the arrows with death, but it's there. Okay, you can. I'm omitting the death from the arrows, but it is there. It should be a vertical figure. Never mind. So you see the model. So it's like it's a mix between the SIR model of Kermack and McKendrick and the SIS model we saw before, because there is demography, but in the end, everybody ends up recovered. Let's say recovered, removed, doesn't really matter, same. But what's important is in the inflow that we had in the SIS model, instead of just considering that everybody's born susceptible, I suppose that a proportion P of those newborns, they're actually vaccinated. And I assume that this vaccination has the effect of moving individuals directly into the R compartment. And because there's no return from R into S, this means they're out of the susceptible population for good. They cannot be infected. So vaccination has permanent effect, and the effect is to remove people from the pool of susceptibles. Those who are not vaccinated, okay, and just a remark in passing, the birth rate, the overall birth rate is dn. Okay, I multiply this birth rate by a proportion. is a dimensionless quantity. I'm allowed to do that. Be careful not to necessarily use rates here. You see the rate is the n, and the proportion is 1 minus p and p. Okay, it's just a remark in passing, because we see many papers, where many models, where people make the mistake. When you're wanting to model something like this is how you should do it. Let me compute R0, and again, I won't get into the details, but we find that the Z3 equilibrium to be everybody's n, so the whole population is susceptible. But if I look at the model with vaccination now, that whole population being susceptible changes. What happens is a proportion 1 minus p of them are susceptible, and the remaining, those who were vaccinated, are in the R compartment. So I get this new disease-free equilibrium. And when I compute the R0, I'm not going to show you the computation, but when I compute the R0, I find that in the case of the first model, I'm finding this. And in the case of the second model, I'm finding something that I can relate to the first one this way. It's 1 minus p times VR0 in the model without vaccination. Okay, so VR0 with vaccination equals 1 minus p, the one without vaccination. And so if I want to eliminate the disease, or I want to drive down endemicity, what I want to do, if I want to make my model with vaccination go to 0, I want to eradicate completely the disease, I need that R0V here to be less than 1, okay, because it's the R0 relative to this new model. But that R0V is less than 1. Remember that we saw that R0V was linked to R0 this way. So this is the R0 for the model without vaccination, and this is the one with vaccination. So yeah, first of all, I should make a remark. Of course, vaccination is always good, except, well, I mean, when it's positive, it always gives you a smaller value of R0. But to control the disease, I want this to be less than 1, which is equivalent to saying that I need to vaccinate a proportion greater than 1 minus 1 over R0. So if I vaccinate that many newborns, I have a situation that leads to extinction. Okay, and this is what we call herd immunity. The idea is that if you think about this well-mixed population of susceptibles and infectious that are interacting together, I've removed many of my susceptibles, and I've made the susceptible infectious, and in this case recovered, interacting together. I've removed a lot of my susceptibles. I've made them infectious, so recovered. And that means that infectious individuals, most of the people they meet, are vaccinated. Okay, and how much do I need to be able to drive the disease away? I don't need to vaccinate everybody. I just need to vaccinate a fraction that is larger than this. So, for example, if you think about influenza, influenza has an R0 typically of 1.5. So if I want to eliminate influenza, of course, I'm not saying in what amount of time I'm going to do so, but if I want to vaccinate, to eradicate influenza, I need to vaccinate 1 minus 1 over 3 halves, so 1 minus 2/3. So with this very simple model, okay, there's a lot of caveats here, but with this very simple model, I would say you only need to vaccinate 1 minus 2/3, so a very small fraction of the population will suffice. Of course, it's much more complicated than this, and this is an approximation, but this notion of herd immunity, I should point out there was early work I mentioned in the history of Math Epi. Ronald Ross has a mosquito theorem where he establishes that he doesn't need to eradicate all mosquitoes to get rid of malaria, only a certain fraction. And so this goes back quite some time. This notion of herd immunity is really, really important.